Hello everyone, happy 2021. In this video, we will be talking about the irreducibility of the polynomial x to the p minus 1 plus x to the p minus 2 plus ... plus 1 over q, the rational numbers. We do need p to be a prime number in this case. It kind of falls apart if it's not. What are the prerequisites for this problem? The biggest thing we need is Eisenstein's criterion. So what we need is we say let f of x be given by an x to the n plus ... plus a naught. So some arbitrary polynomial that has integer coefficients. So these an's are integers. And let p be a prime number such that p divides all of the coefficients except for an. P does not divide an, and p squared does not divide a naught, the first coefficient here. Then if we have all of these conditions, we can conclude that f of x is irreducible over the rationals. The second thing we need is just the binomial theorem. So expanding x plus y to the n, for instance. This is a pretty common question in algebra classes. It does have some nice applications. So for those of you that stay to the end, I'll show one problem that has this as a prerequisite, and I'll give the solution in a different video. Let's get started. So proof, let's assume p prime, and let f of x be equal to x to the p minus 1 plus x to the p minus 2 plus ... plus 1. From here, this is a little bit of a cheap trick, and if you haven't seen it before, it'd be very difficult to figure it out on your own. But let's notice x to the p minus 1 factors as x minus 1 times x to the p minus 1 plus x to the p minus 2 plus ... plus 1. And of course, this is just the same thing as x minus 1 times f of x. So after a little rearranging, this implies that f of x is the same as x to the p minus 1 divided by x minus 1. So that was our first observation. Here comes the next part. This is a very common trick in these irreducibility problems, so it's definitely worth memorizing. And if you get stuck on this kind of problem, maybe try something like this. Set x equal to y plus 1. So seems kind of strange, but you'll see soon that it works out quite nicely. One question you should be asking, though, if you've never seen this before, is why should I believe that if f of x is irreducible, then f of y plus 1 is irreducible? So we'll leave this as an exercise. And let me put the statement here. So let's say f of x is irreducible. And let's say over some field k. If and only if f of y plus 1 is irreducible, or we could call it x plus 1, over the same field k. Proof is not difficult. You just start in each direction and use contradiction. So with this in mind, we're going to set x equal to y plus 1. Then f of x is equal to y plus 1 to the power of p. I'm just making a substitution in star up here. Minus 1 divided by y plus 1 minus 1. So these ones cancel. And this is now where we're going to use binomial expansion. So we have y plus 1 to the power of p. So this is the same thing as the sum from k equals 0 to p of y to the power of k times 1. Oops, I forgot the most important part, the binomial coefficient. So p choose k, y to the power of k 1 to the power of p minus k. Of course, 1 to the power of p minus k, it's still going to be 1. So this gives us y plus 1 to the p. And we're still subtracting 1 off of this. Whole thing divided by y. And from here, it looks a little bit ugly, but let's write out some of the terms in this sum. So when k equals 0, p choose 0 is 1. Y to the power of 0 is just 1, so that's 1, plus. When k equals 1, p choose 1 is p. Y to the power of 1, plus. P choose 2. Y squared, plus dot dot dot, plus we finally get to p choose p, that's just 1. Y to the power of p. So that takes care of what's in the parentheses. We still need to subtract off 1. And let's divide everything by y. Then these ones cancel. And let's divide through by y. And what do we get? We have p plus p choose 2y plus dot 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 plus y to the p minus 1. Taking inventory of what we've done so far, we've said f of x is the same thing as substituting in y plus 1. And out of this, we get p plus p choose 2, blah, blah, blah. And if we can show that this buddy is irreducible, then by the exercise, we're done. Irreducible over q, of course. So the last piece that we need is claim. Well, let's say we have p choose k, then this is divisible by p for all k living in between 0 and p minus 1 inclusive. So maybe proof sketch. We know that p choose k is equal to p factorial divided by k factorial times p minus k factorial. If we were to write out the numerator, this is p times p minus 1, dot, dot, dot. We eventually get to p minus k, and everything after that is wiped out. So we're left with p times p minus 1 times p minus k plus 1, so the term that comes right before p minus k, divided by k factorial. But we know that k is smaller than p minus 1, and this is where p being prime really comes in. We know k factorial can't divide p, so we have a leftover factor of p, and then p divides this expression here. So that's a sketch of the proof. I leave it to you to write out all of the details. But once we have this, if we go back to double star by Eisenstein, and we'll go over this in a moment, f of x is irreducible over q. And if we look at this expression, so this p here is our a naught, this is a1, and the coefficient on yp minus 1 is just 1, and that's our an. So maybe over here, a, or ap minus 1 really, is equal to 1. So p definitely divides p. By our claim, p divides p choose 2. It's going to divide all of these binomial coefficients all the way up until we get to the p minus 1 term. And p doesn't divide 1, so far we've checked off the first two conditions in this criterion. The only thing left is, does p squared divide p? Nope. So we conclude by Eisenstein's that f of x must be irreducible over q. So as we talked about earlier, this is a pretty standard proof, and I'm going to paste here a problem that's kind of interesting. So this comes from an old qualifying exam from UCI. So it says, let V be a vector space over Q of dimension at most p minus 2, where p is prime. Let T be a linear operator on V, such that T to the power of p is the identity transformation. Show that T must be the identity transformation. So maybe it doesn't seem like it on the surface, but we do need to use the fact that this polynomial is irreducible over Q. So Maybe try this one on your own. As another hint, you're going to need to use rational canonical forms. And in the next video, I'll go over the solution. Bye.